The National Electrical Code, or NEC, is a consensus-based code developed by a committee of experts from various industries. These experts include electrical contractors, engineers, manufacturers, and safety professionals. The NEC is updated every 3 years, with the most recent edition being published in 2020. The NEC serves as a valuable tool for ensuring the safety of electrical installations. It is important to recognize that the code is not perfect. Some sections can be confusing or difficult to interpret. Therefore, a solid understanding of the code is essential, and clarification from qualified professionals should be sought when necessary. One significant challenge with the NEC is its sheer size and complexity. The 2020 edition spans over 800 pages covering a wide array of topics. These topics range from general requirements for electrical installations to specific requirements for various types of equipment. This vastness can make it challenging to quickly and easily locate the necessary information. Another challenge arises from the ambiguity in the NEC language. The code often employs vague or ambiguous terms, leading to different interpretations. This can pose a problem, especially for those less familiar with the code or working on complex electrical systems. Despite these challenges, the NEC remains a valuable resource for ensuring electrical safety. By thoroughly understanding the code and seeking clarification from qualified professionals when needed, the risk of electrical accidents and injuries can be significantly reduced. Addressing the suggestion to replace the term ground conductor with bond conductor is a matter of ongoing debate. Some argue that ground conductor is outdated and doesn't accurately reflect the conductor's function. Others believe the term is well established and should remain unchanged. The decision to alter the NEC wording ultimately rests with the code-making panel. The complexity of the NEC arises from several factors. Firstly, the electrical industry itself is constantly evolving with new technologies and practices emerging regularly. The code must adapt to these changes, which can lead to added layers of complexity. Secondly, the NEC aims to cover a broad spectrum of electrical installations from residential to industrial settings. This necessitates detailed regulations for diverse scenarios, each with its own unique requirements and challenges. Thirdly, the consensus-based nature of the NEC development process means that different viewpoints and priorities must be considered and reconciled. This process involves extensive discussion, negotiation, and compromise, which can sometimes result in language that is less precise than ideal. The interpretation of the NEC requires a combination of technical knowledge, practical experience, and a thorough understanding of the code's intent. It is not simply a matter of reading the words on the page, but also understanding the underlying principles and how they apply to specific situations. Firstly, familiarity with electrical theory and principles is crucial. This includes understanding concepts such as voltage, current, resistance, impedance, and power. A strong foundation in these areas enables one to grasp the technical rationale behind the code requirements. Secondly, practical experience in the field is invaluable. Working on real-world electrical installations provides exposure to different types of systems, equipment, and wiring methods. This hands-on experience helps to develop a sense of how the code applies in practice and the potential challenges that may arise. Thirdly, a thorough understanding of the NEC structure and organization is essential. The code is divided into chapters, articles, and sections, each covering specific topics. Knowing how to navigate the code and locate the relevant information is key to accurate interpretation. Fourthly, it is important to stay up to date with the latest edition of the NEC and any amendments or interpretations that have been issued. The code is revised every 3 years, and changes can have significant implications for electrical installations. Fifthly, seeking clarification from qualified professionals when needed is always a good practice. Electrical inspectors, engineers, and experienced electricians can provide valuable insights and guidance on complex or ambiguous code requirements. The debate over ground conductor versus bond conductor centers on the precise function of these conductors. A ground conductor typically refers to a conductor that connects electrical equipment or systems to the earth. This connection provides a path for fault current to flow back to the source, allowing overcurrent protective devices such as circuit breakers or fuses to trip and to energize the circuit. A bond conductor, on the other hand, is a conductor that connects different metal parts of an electrical system together. This bonding creates a low impedance path for fault current, minimizing voltage differences and reducing the risk of electric shock. Some argue that the term ground conductor is misleading because it implies that the conductor's primary purpose is to provide a connection to the earth. In many cases, the earth is not a very good conductor of electricity, and relying on it as the sole path for fault current can be problematic. They contend that the term bond conductor more accurately reflects the conductor's true function, which is to create a low impedance path for fault current and minimize voltage differences. Others maintain that the term ground conductor is well established and widely understood, and that changing it would cause unnecessary confusion. They also point out that the NEC already uses the term equipment grounding conductor to refer to the conductor that connects metal parts of equipment to the grounding system. Ultimately, the decision of whether or not to change the terminology is a matter of balancing accuracy, clarity, and tradition. The NEC is a living document that is constantly evolving to meet the changing needs of the electrical industry. While it may have its challenges, it remains the most comprehensive and widely adopted standard for electrical safety in the United States. By understanding its principles and seeking clarification when needed, one can help ensure safe and reliable electrical installations. Understanding the NEC involves recognizing the different types of grounding and bonding conductors. The equipment grounding conductor, or EG, connects the non-current carrying metal parts of equipment to the system grounded conductor at the service equipment or separately derived system. This provides a low impedance path for fault current. The grounding electrode conductor, or GEC, connects the system grounded conductor to a grounding electrode such as a ground rod or metal water pipe. This establishes a connection to the earth. Bonding jumpers are used to connect different metal parts of an electrical system together, such as metal conduits, enclosures, and equipment frames. This ensures that all metal parts are at the same potential, reducing the risk of electric shock. The NEC provides specific requirements for the sizing and installation of grounding and bonding conductors. These requirements are based on the size of the overcurrent protective device protecting the circuit. For example, NEC Table 250.122 provides a minimum size of equipment grounding conductors for various circuit sizes. It is important to follow these requirements carefully to ensure that the grounding and bonding system is effective. The NEC also addresses the issue of grounding and bonding in different types of occupancies, such as residential, commercial, and industrial buildings. Each type of occupancy has its own unique requirements based on the types of electrical equipment and systems that are installed. For example, healthcare facilities have more stringent grounding and bonding requirements to minimize the risk of electrical shock to patients. In addition to the NEC, other standards and regulations may also apply to electrical installations. These may include state and local codes, as well as standards from organizations such as the Institute of Electrical and Electronics Engineers, or IEE, and the National Fire Protection Association, or NFPA. It is important to be aware of all applicable requirements to ensure compliance. Proper grounding and bonding are essential for electrical safety. They help to protect people from electric shock, reduce the risk of fire, and prevent damage to equipment. By understanding the principles of grounding and bonding and following the requirements of the NEC, one can help to create safe and reliable electrical systems. The NEC also covers specific requirements for grounding and bonding of sensitive electronic equipment. This includes equipment such as computers, servers, and medical devices. These types of equipment are particularly susceptible to damage from voltage surges and electrical noise. The NEC requires that sensitive electronic equipment be grounded and bonded in a way that minimizes the risk of these problems. This may involve using dedicated grounding conductors, isolated ground receptacles, and surge protective devices. The NEC also addresses the issue of static electricity. Static electricity can build up on non-conductive surfaces and discharge suddenly, causing damage to sensitive electronic equipment. The NEC requires that measures be taken to minimize the buildup of static electricity in areas where sensitive electronic equipment is used. This may involve using static dissipative materials, humidifiers, and grounding straps. The NEC also provides guidance on how to inspect and test grounding and bonding systems. This includes visual inspections to check for proper connections and the use of testing equipment to measure ground impedance and voltage. Regular inspections and testing are essential to ensure that the grounding and bonding system is functioning properly. The NEC is a complex and ever-evolving document. It is important to stay up to date with the latest edition and any amendments or interpretations that have been issued. There are many resources available to help one understand the NEC, including training courses, seminars, and online forums. By investing in education and training, one can improve their understanding of the NEC and their ability to apply it in practice. The NEC is not just a set of rules, it is a framework for ensuring electrical safety. By understanding the principles behind the code requirements, one can make informed decisions about electrical installations and help to create a safer environment. The NEC also addresses the issue of surge protection. Voltage surges can damage or destroy electrical equipment and can also pose a safety hazard. The NEC requires that surge protective devices, or SPDs, be installed in certain locations to protect against voltage surges. The NEC provides specific requirements for the selection, installation, and maintenance of SPD. These requirements are based on the type of electrical system, the location of the equipment, and the expected surge environment. The NEC also addresses the issue of harmonics. Harmonics are distortions of the sinusoidal waveform of alternating current, or AC power. Harmonics can cause a variety of problems, including overheating of equipment, nuisance tripping of circuit breakers, and interference with electronic equipment. The NEC requires that measures be taken to mitigate the effects of harmonics in electrical systems. This may involve using harmonic filters, reactors, and other specialized equipment. The NEC also provides guidance on how to design and install electrical systems that are resistant to harmonics. This includes using properly sized conductors, minimizing the length of branch circuits, and using shielded cables. The NEC is a valuable resource for anyone involved in the design, installation, or maintenance of electrical systems. By understanding the code requirements and following best practices, one can help to ensure the safety and reliability of electrical installations. The NEC is not a substitute for sound engineering judgment. It is important to use one's knowledge and experience to make informed decisions about electrical installations. The NEC provides a framework for making these decisions, but it is not a rigid set of rules that must be followed blindly. The NEC is constantly evolving to meet the changing needs of the electrical industry. It is important to stay up to date with the latest edition and any amendments or interpretations that have been issued. There are many resources available to help one understand the NEC, including training courses, seminars, and online forums. The grounding electrode system, as described in NEC Article 250.50, requires all grounding electrodes that are present at each building or structure to be bonded together to form the grounding electrode system. This includes metal underground water pipes, metal frames of the building or structure, concrete encased electrodes, ground rings, and other electrodes. The purpose of this requirement is to create a low impedance path to for fault current, which helps to protect people and equipment from electrical shock. The NEC also requires that the grounding electrode system be connected to the neutral conductor of the electrical system at the service equipment or separately derived system. This connection is made through the main bonding jumper, which is a conductor that connects the neutral conductor to the equipment grounding bus. The size of the main bonding jumper is based on the size of the service entrance conductors. The NEC provides specific requirements for the installation of grounding electrodes. These requirements are intended to ensure that the electrodes are properly installed and that they provide a reliable connection to earth. For example, ground rods must be driven at least 8 feet into the ground and must be spaced at least 6 feet apart. Metal underground water pipes must be bonded to the grounding electrode system within 5 feet of where the pipe enters the building. Concrete encased electrodes must be encased in at least 2 inches of concrete and must be located within the bottom 20 feet of the foundation. The NEC also provides requirements for the grounding of specific types of equipment, such as motors, transformers, and generators. These requirements are intended to ensure that the equipment is properly grounded and that it is protected from electrical shock. For example, motors must be grounded through a metal conduit or an equipment grounding conductor. Transformers must be grounded through a grounding electrode conductor connected to the transformer's neutral point. Generators must be grounded through a grounding electrode conductor connected to the generator's frame. The NEC is a complex and comprehensive document, but it is essential for ensuring the safety of electrical installations. By understanding the code requirements and following best practices, one can help to protect people and equipment from electrical shock and fire. Always refer to the latest edition of the NEC for the most up-to-date information.